this, you should not violate quality of service. I mean, if it's important. So in this case, this is actually important. You know, it's important that you provide fairness and quality of service. So once if you keep traffic in avenue A, and this is green, so this is gonna be always green, and this avenue B is not gonna be green at all, which you're gonna make people here crazy, essentially. So that's cause unfairness, and this is very important that when you design system, you should make sure quality of service and fairness in any kind of scheduling techniques that we're gonna also see a lot in this course when we discuss about memory controller, memory, and other kind of controllers. Okay, but that's kind of a side here. This is the description that your book wants. So yeah, this can be a black box of your traffic light controller that you have TA and TB as input, and these are output, LA and LB. And we have also clock input and reset. So don't forget about reset. There should be always a reset signal for your controller in order to say that, okay, I'm gonna start from this state. So there should be kind of initial state for your FSM that you start from that. By the way, did we resolve the problem in YouTube?
Yes, but there's still an issue with the screen sharing. Can you like stop and start the screen sharing?
So this is also the problem in Zoom.
Yes.
Yeah, just stop and start again.
This one?
Yes. I think when it breaks, yeah, now it should be working.
Okay. So now let's draw the FSM for this controller. So we want to design it more. You can actually also do it Mealy as a homework if you're interested. But Moore FSM is actually very easy for this kind of examples. So we have a state 0 that we consider this is an initial state. This kind of prioritization that you consider that whenever you reset, you start from S0. And in this S0, you consider that output, basically the light for avenue A is green, and the light for avenue B is red. This is your state 0. So as long as we have traffic in A, we're gonna stay in this state. That's the smartness part of our controller. And when there is no traffic, after 5 seconds, we move to state 1. And in state 1, basically we make LA yellow, and the other one is still red. Then from S1, unconditionally, we move to S2 after some time. And then in S2, we're gonna make light for A red, and the other one should be green. And then we need to stay in this state until, as long as we have traffic in avenue B. When there is no traffic, we move to a state 3. Then it's gonna, again, kind of intermediate state that we make the light for avenue B yellow. The other one should be still red. And unconditionally, after some time, we move to S0. This is so easy, right? Any question? Good. So this is, of course, Moore FSM, because your output can be specified only by the state. So whenever you see a FSM and you see that outputs are specified internally inside each state, that's actually is a very good sign that this is a Moore machine, essentially. Okay, so now let's see how we can make a circuit, like implement this FSM in hardware, essentially. So first, we need to start with transition table. So we have a current state and also inputs. Depending on these inputs, we can move to different states. So from S0, if traffic A is 0, no matter, regardless of traffic B, we need to move to basically S1, right? So when it is 0, traffic B is actually don't care here. So this actually truth table is already also considering some kind of simplification, because I mean, you could repeat all. You can say that, okay, 0, 0, 0, 1, for example, but you know that when you are in a state 0, the status of avenue B is not important for you. So you can already put X here, which shows a don't care situation. So you move to S1 after that. And when you are S0 and you still have traffic in A, you want to stay in S0. So next state should be S0. When you are in S1, no, regardless of traffic in A and B, you just go to S2. And when you're in S2, again, regardless of traffic A, but if you don't have traffic in B, you go to S3. And when you're in S2, you basically stay in S2 if you have traffic in B. And again, when you're in S3, you just go to S0. So this is the next state, which shows you the combinational circuit. The combinational circuit needs to generate these output, essentially, based on this current state and also these inputs. So now we need to somehow encode our state. This is one encoding. So we have 4 states here, and we can encode them with 0, 0, 0, 1, 1, 0, 1, 1. We're going to see also other kinds of encoding in a bit. But this is one kind of encoding that basically it ensures that you use less number of flip-flops, essentially, because for this you can only, so your register needs to have only 2 flip-flops, essentially. Then you can, using this encoding, you can actually move it to this truth table, and then you can have S prime 1 and S prime 0, and then you can actually make it more clear, essentially. So from S0, we want to, in this status, we want to go to S1, which meaning that next state should be 0, 1. Now, you need to basically write the equation for each of these outputs. So for S prime 1, we know that from this current state, so we need to check what are ones, right? So basically we know that we go, so this should be 1 when S1 is 0 and S0 is 1, regardless of TA and TB. So this is one of them, S1 prime times S0 and S0, or this state, which is not a state, this combination of inputs, which is 1, 0, X0. So it's going to be S1, S0 prime, and also TB prime. Or this line, which is S1, S0 prime, and TB, right? So this is S prime 1, and also for S prime 0, you can again also see, only write the equation for the ones. You already know that from SOP, right? Sum of the product. So, and then if you can also easily write it. Any question? So this shows actually the combinational circuit that you need to have in order to provide S prime 1 and S prime 0. And this is going to be the input for your next states, essentially. So then you can also simplify it. S prime 1, if you check, you can see that we can simplify these two to S1 and S0 prime. And then it's going to be S1 prime and S0, or S1 and S0 prime, which in the end is going to be XOR. So you can simplify S prime 1 to S1 XOR S0. But S prime 0 is already simplified. Question? Okay, all good. Now we need to do the similar stuff for output. Here, actually, output is very easy because it's a Moore machine. So whenever it's Moore, you can easily generate outputs based on the state. So our truth table is only related to the state. We have essentially 4 states that we encoded them with 2 bits. So we have 0, 0, 0, 1, 1, 0, 1, 1. And for each of them, we need to define the output for LB, LA, and LB. So in S0, we know that it should be green, the light for avenue A, and the other one should be red, and so on and so forth. Then you need to encode output. So for green, for example, we encode it to 0, 0, yellow 0, 1, and red 1, 0. Then you need to basically, add this encoding here. So each of these green, like LA, is going to be 2 bits. So this is LA1, LA0, and LB1 and LB0. And then basically based on this current state, you need to write these values and then you need to write the equation. So for each of them. For LA1, basically we know that it is one only, I mean, in these two lines, which S1 is 1, and regardless of S0. So it's going to be LA1 is equals to S1, essentially. LA0 is only 1 when we have S1 0 and S0 1. So it's going to be S1 prime times S0. And so on and so forth for LB1 and LB0. Is that clear? Yes. Yeah. So S1 and S0 is actually the encoding of our state. So we have 4 states, right? S0, S1, S2, and S3. So when you want to encode them, we use 2 bits for them. S_1, this is not the difference between this one and that is kind of underscore. So S1 is the most significant bit of that state, and S_0 is actually the least significant bit of that. So you are using these 2 bits in order to show your state, essentially. Yes?
So we need to, depending on what encoding we use, implement like the equations, Boolean equations that we have to be simpler or harder, right? So we just have to, if we want the most simple form of Boolean equations, we just have to try out.
So there are actually some automatic way to simplify. I mean, kernel map is actually one of them that we haven't covered. Like in this course, kernel map is actually quite fun, and it can be useful for circuits that they have input up to, I don't know, 5 or 6. Yes.
But I don't mean like just simplifying the equation, but choosing the encoding in a way that the equation becomes. Oh,
okay. You're talking about encoding. Okay. Yeah. Exactly. We're gonna actually have a slide about encoding, and encoding actually affects the simplicity of your design. And there is actually a trade-off between the number of flip-flops that you are using and also the simplification of the equation. So it's actually designer job to decide which encoding is the best. For this one, here is just an example. We are considering this encoding without any discussion, but we're going to also see a trade-off later. So that's a great question, yeah. Any other question? Okay, good. I guess we are not still good in YouTube. Let's make it, do it in break, right?
You can do it one like between now. Just change the thing you're sharing.
I don't know why we have problems today.
Sorry.
Okay. Okay. Yeah, let's continue. So this is also the FSM output that we provided. Now let's see the schematic of this FSM. So this is going to be the circuit that we are looking for, the combinational circuit to generate the next state, the combinational circuit to generate the outputs, and also our state register. So this is the schematic for our state register. We encode our states into 2 bits. So essentially we have this register that has only 2 bits, which is easy. And then we need the schematic for this is really annoying. I don't know what's happening today. Okay. Okay, so to generate the next state, So that was the circuit that we had, right? So we know that S prime 1 is S1 XOR S0. So we have this XOR gate here. And this is also the circuit for S prime 0. So you can, write this, draw this schematic for this circuit. So that's the combinational circuit that we have to generate the next state signals. And also we need to add the combinational circuits for outputs. These are our equations for LA1 to LB0. And we just, draw the gates here. And this essentially is going to be your full circuit. Any question? Okay, good. So let's also quickly check the timing diagram. We're gonna actually look into timing with a lot of details next week, but today just to prepare you for that. First of all, we have, this is basically the signals that we have. So we consider this, there are these clock resets and TA and TB. These are the inputs. And also we have some kind of outputs here. So this S prime 1 to 0 is actually your next states. And S1, 0 is going to be your current state, which is already stored in your state register. And these are your outputs, essentially. So the reset signal that we are considering here is actually asynchronous. So if you think about it, we discussed about synchronous and asynchronous circuits, right, yesterday. So this FSM that we are considering here is actually mostly synchronous because it works with clock. But reset signal is asynchronous, meaning that whenever you just trigger reset, you're going to reset the whole system. So for reset, you don't wait for clock cycle. And that's actually usually the case for many of our circuits today, because reset signal actually comes with a lot of priority and sometimes with some safety reason. So whenever people want to reset, they don't want to basically wait, for any few nanosecond or even lower. So they just want to immediately reset the system. So that's why basically people usually use asynchronous reset. We're going to see how we can actually make asynchronous reset in Verilog that we're going to cover today and next week. But this is something to just prepare your mind for that. So that's why you can see that when we basically kind of assert the reset signal or activate the reset signal, this S prime 1, 0 actually, sorry, the current state after some delay gets to 0. So it doesn't wait for the clock signal. You can actually see that here we consider some delay. So that's actually the case in real life. First of all, clock signals are not that sharp. They are usually like this. So there is a rising edge, which is not completely sharp. The same thing for reset, for other inputs. So usually there is a delay until they get to the high value. And also after seeing each of these basically values, there are going to be some delay in order to get to the value that you're looking for. So here, after seeing this reset, you can see that after some delay, we get to the S0. And this combinational circuit also, the input for S prime 1, 0 also get to S0 after some time. And these are also the outputs that we have, but that also with some delay, essentially. So this one is first. After some delay, we get to this, and also some delay to green and red. So you can actually also continue that. Let me see. Yeah, at this stage that you basically pull down the traffic A, this happened in this, exactly. So yeah, here you don't have traffic A anymore. So this combinational circuit that you have says that, okay, next state should be S1, but that happens in the clock age, essentially. So the next state in your state register will happen S1 in these clocks, in this edge. And also, when it is S1, after some time, this current state, next state should be S2. That's why we have delay here. And then after we wait in S2, and then in this rising edge, we went to the current state is going to be S2. And you can continue that for other basically cases. But we're gonna look into delays and timing a lot next week. So if you don't understand everything here, don't worry about it. Question? Cool. So let's get to this encoding that one of your colleagues also asked. So how do we encode the state bits? There are 3 common state binary encoding with different trade-offs. One is fully encoded, and the other one is one-hot encoded and output encoded. So let's see an example Swiss traffic light with 4 states, green, yellow, red, and also yellow plus red. Yeah, so this is our Swiss traffic light. So essentially we have 4 states, and now we want to encode them. With binary encoding or full encoding, we use the minimum possible number of bits, essentially, which is use log 2 of number of states, bits to represent the state. So here we have 4 states. That means we need 2 bits to encode them. So that minimizes the number of flip-flops, but not necessarily output logic or next state logic. So here is a trade-off that you can assume. With one-hot encoding, each bit encodes a different state. So we use number of state bits to represent the state. We have 4 states in this example. We consider 4 bits. And then exactly 1 bit is hot for a given state, meaning that this is going to be our state encoding, 0001, 0010, and so on and so forth. So that's simplest design process, very automatable. And also the output logic is going to be so easy to design. But you can see that it comes at the price of more bits and more flip-flops, essentially. There is also another way of encoding, which is output encoding, which is possible usually for Moore machine. So in Moore machine, we know that outputs are directly outputs are only dependent on the state, right? So you can basically make it directly accessible in the state encoding. So for example, since we have 3 outputs in light color, we can encode state with 3 bits where each bit represents a color. So here is the example. So we have 4 states. We call it, we can actually have 3 bits here, 001, 010, 100, and 110. And you can see that bit 0 encodes green light output. Bit 1 can encode yellow right output, and bit 2 encodes red right output. So with this, for example, here saying that, okay, both red and yellow should be on. So if you use this encoding, you can actually easily design the output. There should not be any actual logic for output anymore, because your state already shows the output. So that minimizes output logic, but unfortunately, it only works for Moore machines, which is understandable. Why is it the case? Why cannot use it for Mealy machine? Because in Mealy machine, the output is also dependent on the input, on the external input, and you don't know about them, right? So you cannot essentially encode output using your states only. Okay, so in the end, the designer must carefully choose an encoding scheme to optimize the design under given constraints. And those constraints can be number of flip-flops, your output circuit, overall area, performance, power, I mean, many other constraints that you can imagine. Let's also look into the trade-off between Moore and Mealy machine. So we already covered this, that what is Moore and what is Mealy. And for that, we can actually use this example from your book, that we have a snail that smiles whenever the last 4 digits it has crawled over our 1101. So essentially, there is a snail, you can see here, that's scrolling and sees basically bits. Whenever it sees a pattern of 1101, the snail smiles, which is so important, I guess. And then we need to design Moore and Mealy FSM of this snail's brain. So this is the, let's first start with Moore, for example. Okay. So in Moore FSM, so you want to check the pattern of essentially 1101. So you start with this initial state, which is 0. And then you say that, okay, if I see 1, I will go to the next state. If I also see again 1, I will go to the another state, and then 0 to another, and then 1 to another. So meaning that if you see 1, 1, 0, and 1, you get to the state which you know that, okay, I already seen the pattern that I was looking for, right? And then you can encode this state to 1. So this is more FSM because outputs are specified by the states, essentially. There are also some basic transition here that, for example, I can explain a bit more. Here is exciting, for example. So you see 1, 1. If you see again 1, you should state here, right? Because you said, okay, this is 1, 1. I see another 1, so it might be, beginning of another 1, 1, essentially, pattern. So you keep staying here as you see 1. Or for example, after when you get to the final state, if you see 0, you will get back to the reset state. But if you see 1, you actually get back to this state because now you are actually considering that these pattern can overlap, essentially. Meaning that if you have 1, 1, 0, 1, and then 1, 0, 1, this can be actually also another pattern, right? So that's why you, from S4, if you see 1, you move back to the S2 in order to detect these patterns, essentially, overlap patterns. So this is more. But we can also make it Mealy. Now you can see that outputs are actually specified on transitions. So you are in S0, and then as long as you see 0, you will stay in S0, and the output should be 0. When you see 1, you go to the next state, and also the output is 0, and so on and so forth. But here, in S0, S3, when you see 1, you go back to S1 and also make the output 1. Because you don't need to go to another state to say that, okay, I already seen 1 and then output should be 1. You say that I'm in the S3, meaning that I already seen the pattern of 1, 1, 0. If I see another 1, the output should be 1. So I will encode that output actually in the transition. That's actually exactly the sign for Mealy machine. So whenever you have a Mealy machine, in FSM, outputs are specified on transitions, not only the state, because it depends on the state and also the inputs. Is it clear? Question? Okay, sounds good. So what are the trade-offs here? Yes?
Well, I think you can do the same stuff with more Mealy, but with more, you might need more different states.
Great. Yeah, that's one of the trade-offs. More FSM always has higher number of states. So that comes with some overhead. But is there anything that we think Moore is better than Mealy? Yes?
It's easier to encode.
It's easier to encode program, yes. It's easier to sometimes to reason about it also. But there is also another very important thing about Moore, which you guys seen a kind of glitch in previous lecture, right? Do you remember? There was an input that there was a glitch, very short pulse. I don't know if you remember. So usually in Moore FSM, in Moore machine, your outputs are much more stable. And that's very important because the output is defined by the state register, and a state register are actually stable because they are registers, right? But in Mealy machine, your output is actually is calculated based on the state, which is stable, and also the inputs. But inputs may not be stable enough. So there might be some glitch, some high pulse, which is just very, I would say, short term. It should not happen, but that happened because of some timing issues that we're gonna also see more next week. So if that glitch, for example, happens, your output's gonna also see a glitch, which is not good. So in Mealy machine, usually people observe that outputs may not be that stable enough. Also, in Mealy machine, you have a long combinational circuit from the input to the output, essentially. So in general, in design, people try to actually minimize the cycle of combinational circuit as much as possible. So in Moore machine, that's good because you have a short combinational circuit to generate next state, and also another combinational circuit which takes input from only a state. But in Mealy machine, you have input to the output. And assume that you combine several Mealy machines together, then you have a very, very long combinational circuit, which can actually makes you crazy when you want to design it. Yes?
Since flip-flops are so expensive and Moore needs more states, can you say that it's usually from, if you want to minimize the amount of transistors that we use in Mealy communications and all?
I should say that maybe in the past, yes. Yes, of course. When you really, that's your main effort to reduce the number of flip-flops, probably you should go with Mealy. Yes, Mealy. But first of all, the cost is actually overall, because sometimes your output logic might get more complicated when you have Mealy. Also, the costs for flip-flops are not that high in today's technology. So it's easier, you can make flip-flops. But yeah, I mean, it depends on the current technology as well as also the trade-off that you're concerned. Yes?
But you don't need to use flip-flops, right? You could use some simple way of storing the bits.
So, yeah.
More efficient.
That's true. The things that those memories, like SRAM, DRAM, and those that they are simpler, usually they are not used for such circuits, essentially. So we're going to see about that later. But for example, the registers that we have inside the processor, they're actually flip-flops. Okay. You can design flip-flops a bit easier. I mean, with less number of transistors. There are a lot of research on that people make flip-flops with less number of registers. Less number of transistors. I don't know why you said register. Less number of transistors. But overall, the cost of flip-flop is much higher compared to SRAM and DRAM also. Cache, like in the processor architecture, caches, for example, they are SRAM. Like you have also main memory, which is DRAM. But the register file and registers that the processor has, usually they are actually kind of flip-flops. Flip-flops are very good for synchronization, essentially, because they work nicely with clock. Question? Okay. Yeah, so we summarize kind of the trade-offs between Moore and Mealy. But in the end, unless we specify explicitly in the, for example, exam question that you should design Moore or Mealy, you have that freedom, to design it Mealy or Moore, or the way that you like it. Okay, so that's a procedure for FSM. We kind of summarize. We determine all possible states of our machine, and we develop a state transition diagram. And generally, this is done for a basically textual description. And you need to determine the inputs and outputs for each state, and also figure out how to get from one state to another. And let me finish this, and then we can take a break. And as an approach, we can start by defining the reset state and what happens from it. This is typically an easy point to start, and then continue to add transition state. So yeah, and then building an FSM is like programming, but it's not completely like programming. And FSM has a sequential control flow, like a program with conditional and basically how to like go-tos, essentially. Okay. So in the end, we're going to use these FSM in order to, for example, design control logic. FSMs are really good for designing control logics. And in today's machine, it's a modern computer system, we have controllers everywhere. So we have a controller that controls the microarchitecture of the processor. We have controller to control, for example, your memory controller, your caches, your storage system. There are many, many controllers in the system, and people use different FSMs. So there might be also a way that you combine all these FSM and make a quite big FSM with millions of states in order to control the whole system. But usually the way that people design is that they design disjoint FSM, and these FSM needs to somehow communicate to each other. So that's the way that people make bigger state machine. So we're going to see a lot about processor design later in our future lectures. Okay, so we are done with the first part of today. So let's take break and get back when the ring bells. And we will continue with lab and other stuff. But
Okay, let's get it.
for reliability and also for power.
Thank you for sitting.
Because whenever there is a
Delivery. Thank
there
you.
needs to be some charging.
Here, thank you. Leave it on for now, but okay. Let's go here.
Now? Or you can hear me now, Manos? Manos, now?
We can hear you.
Can you hear me?
Yes, Constantinos.
Okay, let's get started again. Is everything going fine on Zoom, YouTube? Yeah, we had some infrastructure issues, but things are, I guess, under control. Thanks to our great TAs. Great. So I think this is also a kind of lecture that you guys you've been waiting for it. I'm going to introduce you the labs and also provide some FPGAs. I put Atterberg's name actually here on purpose because he's the main person for labs and he's leading labs. He's also attending this conference to present HPCA conference, as I said, to present his paper. So yeah, but in general, if you have questions about labs, you need to, I mean, you can of course come to me, but Atterberg is the main person essentially. Okay. So we're gonna see about logistics first. Our lab session, you know that is on site and we have 4 days. This information is already known for you, so I'm not gonna bore you. And basically we have these times and also these rooms. Just make sure that in Friday, the first session, we have different rooms. So this should be easy for you to cover. And the first session is going to be next week on Tuesday, so make sure you attend. I mean, those people that are going to attend Tuesday session, essentially. And you know that you will work in groups of 2. We had 2 options, which I think we are already aware of that, so things are already defined. And every group will receive an FPGA board to work with, so make sure that you attend the first week of the lab. I mean, you should attend all the lab sessions, but first week is also important because you're going to get FPGA. And please follow Moodles for details. The grading, we have 10 labs and we have 30 points in total. So you know that 70 points is coming from your exam and 30 points is coming from your labs. So with that, we're gonna have 100 points that is gonna somehow scale to 1 to 6. So we will put the lab manuals online on our webpage. And this grading policy, we have in-class evaluation, like lab sessions, evaluation, which is 70%. And mandatory lab reports, which is 30%. And there's going to be 1 point penalty for late submission of the report. So you should finish the labs within 1 week after they are announced. You can also use your grades for labs from past years. This, for example, the Moodle page for last year. We had actually, in the past, we had the students that, for example, in 2023, they wanted their lab grades from 2019, you know. So don't worry, we have database we can fetch from, I don't know, whenever you want. Just let us know exactly, essentially. And for question, you can email us using this basically mailing list. This will email sent to all TAs, essentially, that we can. And also, we're going to have Moodle Pro. So what we will learn in these lab sessions, we're going to see about this transformation hierarchy, and we're going to understand this software-hardware interface, microarchitecture, and logic, specifically labs. So, and how to make trade-offs between performance and area complexity in your hardware implementation. There are hands-on experience on hardware prototyping using FPGAs, and debugging your hardware implementation using hardware description language, HDL, which specifically, we're going to see Verilog, how to use it, and this hardware design flow, and as well as computer-aided design tools, short as CAT tools. So what is an FPGA? FPGA stands for Field Programmable Gate Array. This is one example of FPGA. There are many, many different examples also in the market, in the world. You can see FPGA is a software reconfigurable hardware substrate. That makes FPGA so exciting because there is a chip, but that chip is not hard-coded, essentially. So you can implement kind of any circuit, as long as your circuit can fit in that FPGA, because each FPGA has limitation in the number of lookup tables, number of, I don't know, flip-flops, multiplexer, whatever. So each FPGA has a limit, but within that limit, it can implement everything that you want. So this has reconfigurable functions, reconfigurable interconnection of function, which is very, very important. We're going to see a bit why, but you have a lot of switch boxes. You have a lot of switches that they call switch box, connection box, and all these switches can be reconfigured in order to connect a logic block to another logic block, which is very important for FPGA to implement your circuit. And also we have reconfigurable input and output in FPGA. So you have already seen this slide from Professor Mutlu's lecture that essentially we have this flexibility from CPUs, and this is quite programming ease. But as we go through this basically spectrum, you're going to see more efficiency, but at the same time, you might have basically less programmability. So FPGAs they are standing kind of in middle between complete ASICs and also something also after GPUs, that they are accelerators. So we have FPGAs in today's system. These are some slides that I just want to motivate that FPGA that you're going to use, not exactly the FPGA that you're going to use, but the concept is very useful, and many systems are actually using FPGAs, modern FPGA. This is one example that used for deep learning platform for FPGA. And this also from another system that they use FPGA to solve complex science, engineering, and business problems that require high bandwidth, enhanced networking, and very high compute capabilities. There's also another FPGA used for DNA sequencing, which is important for genome analysis. Bioinformatics, you may know, when you want to, that can actually provide a lot of applications, including personalized medicine, to also, mitigate this outbreak of our disease. So all these are important in genome analysis. And DNA sequencing is also one of the very, very early step of that. So FPGAs are very useful for that as well. And we have also in our group, we have used FPGAs in many of our studies. These two papers, Gatekeeper and Sneaky Snake, both of them are actually FPGA-based accelerators for bioinformatic applications. And you can learn more about it by checking this paper. We also use basically FPGAs for other applications. Again, this also base color is for genomics. We also use FPGA for weather prediction, stencil applications. So these are different applications that essentially you can use FPGA to accelerate them. You don't need to know all details, of course, about them. Just these slides are here just to motivate you to see that how FPGAs can be useful to improve performance. In our group, we have developed a system called, in the past we were calling it SoftMC, but we actually extended much more and we improved it, and now the name is actually DRAM Bender. Ataberk is the leader for this project actually, so that's why he's also your head TA in these labs. So this is an open source FPGA-based infrastructure to experimental studies on DRAM. So you can actually do a lot of studies on DRAM. We're using this DRAM Bender, which is kind of, for example, you can play with all timings of your DRAM, your commands that you're sending to DRAM. And that can help you to understand many of the hidden stuff in your DRAM and also design techniques in order to benefit from functionalities that they are actually already available in DRAM, but people may not be aware of that. So for example, in one of our recent work, we show that commodity off-the-shelf DRAM chips, they are capable of doing computation. They are already capable of doing functionally complete Boolean logic. So you know what is functionally complete, right? So you can implement NAND, NOR, AND, OR, and NOT operations using commercially off-the-shelf DRAM chips. So that's what we, for example, got from this DRAM Bender system. So you can also, if you're interested, you can check SoftMC and DRAM Bender on our GitHub page. It's already completely released. And this is also the paper if you want to learn more about it. This is also one of a picture from this system, you can check. And this RowHammer study, that the first paper that we published in this area, that we show that essentially by opening and closing or activating and deactivating a row in a DRAM row, multiple times, or let's say fast enough, you can actually cause errors in adjacent or neighboring rows in DRAM. So that's a phenomena. We called it they called it as RowHammer. It's called as RowHammer. That basically breaks one of the main importance, like this isolation principle of DRAM chips. So you can actually, by activating and deactivating one DRAM row, you can cause errors. And later works, they use these phenomena to actually design attacks, security attacks. So this is RowHammer that you probably know about it because from Professor Mutlu's talk. But basically, we use our system to have a lot more deeper look in RowHammer and also uncover a lot of stuff about RowHammer, as well as one of the technique that basically industry provided, and they actually claim that this solved the problem, RowHammer, but later on with this work and other works, we show that this is not the case. So yeah, essentially, you can use this kind of DRAM vendor infrastructure to do a lot of studies. There's also another work that we published in 2023 that we show that actually that there is also another phenomenon called row press. We actually call it row press. That if you keep one row in the DRAM active for a long time, that can actually cause errors in neighboring rows. So we call it row press, and we also again use DRAM vendor. You can, for example, generate random numbers inside your DRAM, and random numbers are important for many, many applications. So we get to this, generation of random numbers in DRAM using this DRAM vendor infrastructure. Okay, so I don't want to bore you more, but this kind of infrastructure also can be used for other memories. For example, this one is for characterization of flash memories, and it's actually from quite past. In 2012 until 2018 or so, that we had this kind of infrastructure that we studied flash memories. And we uncover a lot of reliability issues as well as mitigation techniques for all these reliability issues in the flash memories of that time, essentially. If you want to learn more also about flash memories, like this error characterization of flash, I would recommend you check this paper. Flash memories are really exciting. It's actually one of the very, I would say, nice lesson for every researcher. Because when people were working on flash memories in 1990 or so flash memories are way behind of their performance back then. And there were many people that were saying that, why you're working on this kind of technology? This is not gonna work at all. And but now you can see that those people were completely wrong. So you had to actually work on these emerging memory technologies to make them possible that can actually change many people's life. And now the main reason that, for example, we have smartphones is flash memory. Otherwise, you could not, for example, have a hard disk drive in your smartphone, and then gets, that rotate in your pocket to have your memory, essentially. So it's very interesting to see why we need to work on emerging memory technologies. Okay. You can also use FPGAs a lot for prototyping. This one example that we designed a prototype in order to use processing using DRAM. So we showed that, for example, we can have a holistic end-to-end FPGA-based framework for processing in DRAM, that you use your DRAM in order to do computation. You may not know completely what does it mean exactly, but essentially you are using your DRAM to do computation. And these PyDRAM, you can actually implement them in a prototype. The whole system is closed. You can see, you can implement the whole system essentially. Okay. And these are also for another work, MetaSys, and you can see that Atterberg here, this guy. He got this best paper award at HighPeak for this work. Okay, so let's have an overview of our lab exercises. Any questions, by the way? Good. So this is our FPGA board, basis 3. This is actually not a bad board. I mean, it's quite capable, but of course, it's not as capable as modern FPGAs that people use. But you can learn a lot of fundamental things about these FPGAs. So there are many actually stuff going on this FPGA board. You have USB connection, you have video out, VGA, you have micro USB, you have power switch, you have 7-segment displays. These are a lot of LEDs that you have. You have switches that you can control, use them as an input, for example. You have push buttons. And this is your FPGA chip. This shows that, you know, when you want to design a system, there are the brain actually usually is so small, and there are many, many things going on, you know, around it to make interface. And that's why actually interfaces are actually very expensive in the computer system. Okay, so at the end of exercises, we will have built a 32-bit microprocessor running on the FPGA board. So it will be a small processor, but it will be able to execute pretty much any program. So I think this is very exciting that we will learn how to design a microprocessor. And each week we will have a new exercise that in the end will guide you to that microprocessor essentially. So you're also encouraged to experiment with the board on your own. We may have some extra boards for those who are interested, unlikely. I would emphasize on that, but you can ask, of course, and we see. And it's not possible to destroy the board by programming, so don't worry. Okay, so in lab 1, we're gonna draw a basic circuit. It's gonna be about comparison. So you just need to draw a schematic of that circuit, and we don't have FPGA programming involved in lab 1. But we encourage you to do it later when you have understanding of FPGAs. In lab 2, we want to map our first circuit to FPGA. We're gonna start with addition, which is very simple. And we design a circuit that adds 2 1-bit numbers, which is gonna be a full adder, and then we reuse this 1-bit full adder in order to make 4-bit addition. And essentially, you need to implement design a FPGA board and you use input switches that I showed in that picture. There are some switches that you can use as the input to the FPGA, and also the output of the FPGA goes to LEDs. So you can see the output on those LEDs, you know, based on the lights that they are lighting. In lab 3, you're gonna use actually 7-segment in order to show the result of lab 2, essentially. So that's training you how to design a combination of circuits for FPGAs. In lab 4, we're gonna design a finite state machine that we design these blinking LEDs for a car's turn signals. And this implements and basic implementation and use memories because it's kind of a sequential circuits. And also we should be able to change the blinking speed. So you're gonna see in your lab material essentially. In lab 5, we're gonna see how to implement an ALU. And that's actually the first kind of a step in order to get to your processor. So you will design your ALU that can do some arithmetic operations like addition, subtract, multiply, compare, and some logical operations like AND, OR, and so on and so forth. Then in lab 6, we're gonna test our ALU. Basically, whenever you design, you need to verify it. And that's the verification part, that you need to design kind of test bench to simulate your design. And in lab 6, the focus is to teach you how to simulate and test the functionality, essentially. So we learn how to debug your implementation and to resolve problems, essentially. In lab 7, we're gonna write an assembly code for the microprocessor that we are looking for. We will use the MIPS, and that implement a program which you will later use to run on your processor, which it sounds quite exciting, at least to me. In lab 8, we will basically make this full system integration. We will this will cover in 2 weeks. So essentially, we have 10 labs, but lab 8 is actually kind of 2 labs. So we have lab 8.1 and lab 8.2 essentially. And then we learn how a processor is built, and we will complete your first design of a MIPS processor, and we run a snake program on it, for example, like this. Okay, and in lab 9, we analyze the performance of the processor that we design and how we can improve the performance by adding some other instructions like multiplication, bit shifting, and so on and so forth. Okay, so that's all. But you can see the material for every lab. We will put it on website. You will check it. I encourage you to check it early enough, and you attend the lab session by kind of, prepare mind as much as possible. Okay, we also provide a bit more detail about the FPGAs. So what is an FPGA? We already know that it stands for Field Programmer Gate Array. And you know this stuff. So this is a high-level overview of FPGAs that we need to configure logic blocks. So all these rectangle squares, let's say, they are kind of logic blocks that you need to configure them in order to implement some functions. And then you need to configure also these switch boxes or switch blocks, essentially, in order to make connection of these circuits. And then you have some IO blocks, and basically that you can use them. You can, again, also configure them in order to see the output. Like when you check the data sheet of FPGA, you know that you're going to see that, for example, some of these IO paths, they are connected to some outputs in your board. Like some of them are connected to 7 segments, some of them are connected to, for example, LEDs, some of them are to switches. So you can actually configure them nicely. There are 2 main building blocks in FPGA: lookup tables and switches. And I mean, you already know about lookup tables. It's a memory that you can implement. Like when you have a LUT of 3 input, you can essentially implement any 3 input function using that LUT. So, and then also you have switches that you can configure them in order to make connections, essentially. So this is a 3-bit input LUT that provides 1 bit output, and it can implement any 3 input function, as you know. So this stuff, I think, is already familiar for you from the lectures of Professor Mutlu. And then essentially you can combine these LUTs in order to, this is still 3 input. But how to implement complex function? We need FPGAs are composed of many LUTs and switches. So in the end, yeah, this, for example, is a FPGA chip, and this small dot is actually this, for example. So you have a lot of these, and then you need to basically combine all these LUTs to create bigger function. For example, if you have 3 input LUTs, and your function is 4 input, so you can think of how many 3 input LUT you need to use in order to make a 4 input function. Think about it. But yeah, so modern FPGA architecture, they typically use LUTs with 6-bit. So there are 6 LUTs, and we have thousands of them. And we have megabytes of distributed on-chip memory, that all these on-chip memory are essentially used to configure LUTs and also switch boxes. So whenever, for example, you want to configure this switch box, for example, here to connect this wire to this wire, you need to somehow configure it. And there are small memories that you can actually configure each of them using a bit string, and that makes that connection happen, essentially. So yeah, exactly. This is for on-chip memory, but at the same time, for better efficiency, FPGA also has some hard-coded special purpose hardware blocks. For example, multipliers are usually very expensive, and if you want to implement multipliers with LUTs, their performance might not be good. So there might be some ASIC special purpose hardware blocks for multipliers. And whenever, for example, you have a multiplayer in your design, you just use that, for example. Modern, basically, FPGA, they might have also processor. So there might be some microprocessor on your FPGA chip, or also beside your FPGA chip. Yeah, exactly. Even a general purpose processor can be embedded within the FPGA chip. And this is an example of modern FPGA platforms, Xilinx Zinc UltraScale Plus. And again, this kind of advantage and disadvantage of FPGAs that, you know, essentially, as advantages, we can say that an algorithm can be implemented directly in hardware, and we have high specialization, high performance, and high energy efficiency. We have low development cost, of course, compared to custom hardware design, which is ASIC, for example. And we have short time to market, and usable and reusable for many purposes. So that's why FPGAs are quite useful and widely accepted. But of course, they also have disadvantages. So they are not as fast and power efficient as dedicated hardware customized for an algorithm. And reconfigurability comes at a cost, significant area and latency overhead, as well as, I would say, reliability overhead as also. So there are all these switch blocks, and you are controlling all these with some memories. So if something happened in that memory, for example, 1, 0 goes to 1 or the other way around, then the whole circuit is just can be wrong, right? So there are a lot of reliability issues that also can happen in FPGAs, as well as other circuits, but that's also one of very important things to know about FPGAs. Yes?
So the latency overhead, would you say that it's usually still faster to run a FPGA than on general purpose?
I would say usually yes. Yeah, that's usually the case. Specifically because on a general purpose processor, you have this sequential program. So there is this stuff that, I mean, even though you can also have some parallel programming, but still there is a program that there are a lot of sequential instructions that you need to go over them one by one. But FPGAs are kind of, they are assembling hardware, which has a lot of concurrency. So that's why, in general, their performance is much better. But at the same time, they comes at the cost of the stuff that I mentioned. And also their performance is not as good as ASIC and custom devices. Yeah. Very good question. Yes.
But if you already have some sort of, for example, like some specific part of the chip that's dedicated to some tensor operations.
Yes.
Is an FPGA still faster because you can kind of adapt to the algorithm on its own?
No, probably no. Yeah, usually, so yeah, I mean, that's the thing actually. Today's systems are actually heterogeneous. And they are using general purpose cores, they are using GPUs. In GPUs, they also have tensor cores kind of customized for that application. So actually today's system are combining all these different basically platforms. So in a modern system, we have CPUs. Actually, this is also, as Professor Mutlu also mentioned, this shows Apple M1 chip, which has GPUs, has also general purpose cores, FPGAs, maybe not FPGA, but many other accelerators as well. So basically today's system are combining all these. And that's why, because we need, there are not every application can be accelerated in either of them. So there, you need to benefit from the all these things together, essentially. Yeah. Any other question? Okay, great. So to program an FPGA, we are using computer-aided design or CAD tools. FPGAs have many resources, LUT and switches, and they are hard to program manually, of course. So it's going to be very headache if you want to do that. So how can we represent a high-level functional description of a hardware circuit using the FPGA resources? And then we need to select the resources to map our circuit to, and then optimally configure the interconnect between the selected resources and generate a final configuration file to properly configure an FPGA. So if you don't have CAD tool, we need to do everything manually. But luckily, we have CAD tools that we have this problem definition, and then we use kind of hardware description language like Verilog and VHDL, which you're going to see in a bit. So that's your job, or our job. But after that, we will use CAD tools. So there is this logic synthesize that synthesize your Verilog programming essentially to logics. And then there is this placement and routing to place your logics on all these FPGA configuration blocks, and then how to route them by configuring all these switch blocks. And then after placement and routing, we will get to this bit stream generation that essentially that bit stream needs to flow to your FPGA and configure every single LUTs and memory that you have on your FPGA. So after this bit stream generation and that communication, you're going to have your circuit on your FPGA essentially. And that is automated, luckily, fortunately, with different tools. But in this course, we're going to use Xilinx Vivado tools. So Vivado is a software tool that helps us throughout FPGA design flow. And this provides tools to simulate also our design, to validate the correctness of the implementation, debugging, and many other things. Also, Vivado also provides drivers and graphical interface to easily program the FPGA using a USB cable. And it's this application already installed in computer rooms in our lab rooms, essentially. So you can also check basically tutorial of this Vivado using this basically video. I'm not going to play it now, so you can play it at home. Apparently, I'm supposed to play it, but yeah, I would skip it. Okay, so keep in mind that you do not need to install Vivado on your laptop. I mean, you can do it if you want, but lab PCs already have it installed. And please do not ask PAs to grade your labs outside of lab hours, and submit your lab files in the correct format. So the format is already specified in your lab manuals. And please double check your uploaded files and do not incorrectly submit, because that can cause 0 points for you. And double check your grades, essentially. So when we want to finalize your grade, we will send an email to remind you, but very important that you check your lab grades by then and let us know if something is missing. And then we can fix that problem in time, hopefully. Okay. So that brings me to the end of this lecture, but I want to also talk a bit, start at least Verilog very quickly, just to give you some food for thought, and then we're gonna continue Verilog next week. So can we go to lecture 4C? Manos? Can we go to 4C? Okay, sorry. I think you can handle it. Okay. Is all good on Zoom?
The entire screen. That's what we did before.
Is it okay? Entire.
The entire screen.
Okay. All good? Okay, so we have 12 minutes. Of course, we cannot cover this lecture, but we're gonna see a little bit about this. So yeah, this is the agenda for not today much, but yeah, anyway. We will basically we want to get to this processor next week and the weeks I guess after, how to design a processor. But now let's also quickly talk about hardware description language and Verilog. First, I want to use some pictures to motivate why we need that. So this is a chip in 2017, which was one of the strongest chip back then, and it had 1.75 billion transistors. So people were kind of, what we're gonna do when we have billions of transistors. And nowadays, actually, we are way away, from that. So in about 47 years, we have basically 1 million-fold growth in transistor count and performance. This is also another chip in 2021, which has 16 billion transistors. This chip is in Apple M1 Ultra in 2022 that has 114 billion transistors, which you can see that it's growing and growing. So of course, it's not easy to configure every single transistor, by our own. So that's why we need some, tools for that. There's also Cerebras in 2019 that has 1.2 trillion transistors. And largest GPU back then had 21.1 billion transistors. And another version of Cerebras Wave Scale Agent 2 has 2.6 trillion transistors. And also we also checked what Wikipedia says about it. And as expected, memories are actually having way more transistors. So like flash memory in 2022 has 5.3 trillion transistors. Or for example, GPUs in 2022 had 80 billion transistors. So you can actually see that here is also very important. So the DRAM includes about 12 quadrillion, it's 1,000 of basically trillion transistor, and that's about 97% of the whole transistors. So that shows actually that most of our systems transistors are actually spending on memories. So make sure that you always memorize that basically memories are actually very, very expensive in terms of number of transistors. Okay, so how to deal with this complexity? We are using hardware description languages, and what we need for hardware design that provides ability to describe and specify complex designs and to simulate their behavior, functional timing, and to synthesize using automatically design as we showed, like Vivado as a CAD tool, basically. So hardware description languages enable all the above, and there are designed for basically describe hardware, and we have different version of it. They called as HDLs, but Verilog VHDL are the most common HDLs. People actually, both of them are useful, but in this course we're going to learn about Verilog. And of course, if you learn one, it's not hard to learn the another one. Okay, so as I said, there are two well-known HDLs, Verilog and VHDL. Here we provide some history about it that you can check if you are interested, but that's not the most exciting thing that you can bring from this course. Okay, so why specialized languages for hardware? So HDLs enable easy description of hardware structures. So specifically, you can think of using, why not using, for example, C programming, to specify hardwares. The reason is that, HDLs are customized for hardware. And in hardwares, we have some basically components, like we have wires, gates, registers, flip-flops, clock, rising, falling edge, and all these basically components or specification that they are not necessarily provided in sequential programming, like the C++, for example. So that's one reason. Another reason also is to enable basically parallelism. So in hardware, we have a lot of concurrency. So every single, actually all these transistors, all gates, they are actually operating in parallel. So there is no sequential thing happening in your design. So that's why actually, if you want to model your hardware using, for example, C program or using Python, it's going to be very headache because it's very hard to simulate that parallelism. And that's why actually our simulators that people develop, for example, a simulator for GPU using C++. These simulators are very hard to design, and also they are really slow because so they need to actually simulate all this complexity and all this concurrency that we have in the hardware, which is not the easy thing to do. So HDLs enable that, and all hardware logics can operate concurrently in HDLs. And both of the above is specification, simulation, and synthesis for your hardware. So HDLs, basically we have some key design principle that we should consider. We have this hierarchical design that we always need to design a hierarchy of modules for our system. So in a complex circuit, you actually have, you can see that there are many blocks, but each block actually can be basically structured by many gates. So we use some predefined, we call them primitive gates, like AND and OR. These are actually some kind of leaves in your hierarchical design that you don't need to go below. Yes?
The free cache, that's SRAM, right?
Yes. Yeah. And simple modules are built by instantiating these gates, like components like multiplexer. So we're going to see more about it later. So basically, you need to make a hierarchy of your design. So you can have a top-down approach that we're going to see in a bit, or bottom-up approach to design your big system. So top-down approach, you have a top-level module, which, for example, your top-level module is, let's say, microprocessor. But then you're going to say, okay, my microprocessor would have some sub-modules. And then you need to design each of these sub-modules. But each sub-module also can have some sub-modules, and then you're going to get to some leaves. And these leaves are actually your primitives, the one that you don't want to go below of that. For example, in Verilog, you can say that, okay, my gates are those leaves. You may combine some gates and make some bigger logics, like, for example, adders, multiplayers, and then you may consider adders or multiplayers, all these arithmetic units as your leaves, essentially. But anyway, there going to be some instance that you don't want to go below of that. And this is a kind of top-level methodology that you might have. You can also think of bottom-up design methodology, that you first identify the building blocks that are available to you or to us, and then we build bigger modules using these building blocks, and these modules are then used for higher-level modules until we build the top-level module in the design. So you can also go the other way around. And I should acknowledge that in our system, so as a designer, whenever you want to design a system, you actually need to use combination of both. So you need to have kind of top-down approach first, because you should be motivated to what you want to get. But then when you want to implement, you usually use the bottom-up approach. So you design you make this hierarchy using top-down approach, but from the implementation-wise, usually go bottom-up. So in order to define a module in Verilog, so module is the main building block in Verilog. That's a notation. We first need to define the name of that module and directions of its ports, like input and output. So this is an example module that we have, and it has 3 inputs, A, B, C, and output Y. And then we want to describe the functionality of this module, essentially. So this is the example Verilog code for that. You start with definition of the module. You say, these are keywords, essentially, module, and then the name of module, which is example. And then you have these port lists, A, B, C, and Y. These are ports. And then basically you need to define which of them is input, which of them is output. So here, for example, A, B, C are inputs, and Y is your output. And then basically this part, you need to specify the functionality of that module. And in the end, you have this end module, which close your block. And also, you can also have different style. So these 2 definitions, both are correct. So here you say that module, for example, tests A, B, Y, and then you say input A, input B, output Y. You can also say module test, input A, input B, and output Y. So both are correct. And it depends on your style, the way that you want to write. So what if we have multi-bit input and output? We can define using this kind of range. So you put range end and range start, and that shows the number of bits you have. So number of bits is actually range end minus the range start plus 1. Example. So for example, here you have input 31 to 0, A. That means that actually A is actually a value which is 32 bit. And then you can specify every single of bits of A using this notation. A31, A30, A0, and so on and so forth. You can also do, for example, this B1. You don't need to put 0 always. You can say that, for example, output 15 to 8 B1. And this basically B1 has 15 until B1 8, essentially. This is also another example, 7 to 0, and you can see. And you can also have this input C, which is single bit signal. So here, when you say 31 to 0, actually it represents a 32-bit value. So we prefer actually to define it as is. But you can also define it as 0 to 31A. But That's not very common to use when you want to define a multi-bit value. You usually use this kind of notation, 0 to 31, when you want to resemble kind of array definition. So you have the array and you want to define every bit of it. Okay, so, and it's also good to be consistent with our representation, multi-bit signals. Always we can use this kind of notation. And for whenever you want to define an array, you use this kind of notation. Okay, I think it's a good place to stop. We will continue Verilog next week. Have a nice weekend.